to present the work as following to me. Let us look at the slide. The basic text of the theory of deformed space. In the slide, there are other two images of the very first experiment of the neutron and the so-called piezonuclear neutrons. The photos refer to two different research centers and in a period that goes from 2007 and 2009. The experiment results were published for the first time in 2009 in the scientific journal Physical Letters. What is the connection with the three images? The experimental results are perhaps the first and most obvious evidence of a nuclear obtained by following the lines indicated by the deformed space-time theory. This is important for this connection. The imagine, you can see the imagine of our friends Cardone and created. And the imagine refers to a center, an old center of research, and on the left to the center of Niagara. Now, having in mind the theory of the deformed space-time that certainly helps us in understanding this new kind of phenomenon, we prefer to use the term deformed space-time neutrons, DST. DST neutrons for a long time piezonuclear origin.
If you could speak just a little louder, I know I'm having trouble over here, so maybe people in the back call a bit more so.
Yes, DST neutron emission have been repeatedly observed and measured over several years and in numerous examples. Briefly, the main activities performed: extensive excursions, measurement of weight by means of bubble detectors, cavitation solution hydrochloride, by applying to it ultrasonic and mechanical vibrations, and Newton measurement performed by means of boron trichloride and the CR39 passive detectors. Main Newton measurement obtained onto the night test specimen, cavitation iron salt water solution with different concentration and different sand powder, measured by Newton passive bubble detectors. Sonication of IEC 304 steel bar producing asymmetric Newton emissions, and in the end, Newton detection by means of microspect 2 Newton spectrometer. In this, there are some pictures. We can see a trifluorura trifluoride. This is a press with a bubble detector contained a round the specimen to be pressed. Bubble detectors. Note that the bubble detectors were not done at the time held in high regard by the scientific communities, but in a short time detectors began to be used even by the most famous physicists. So, right, and so let's go. Oh, this is very important. In all experiments that have been carried out so far, the neutrons detected have the following peculiar characteristics. They are emitted in bursts, not in a constant pulse. The direction and of emission are not fixed but change in space. The neutron emission is asymmetrical, anisotropic, and with no fixed time. No gamma emission accompanies the emission of these neutrons. Oh, some images of the asymmetry and energy of neutrons at various angles. The same thing in ours, but we reported the passive detectors of CR39. This is not CI39 simply, but modified by us. We see, of course, some anomalies. Difficulty even in detection. It should be stressed that not always commercial available instrumentation, often designed for purposes of sanitary protection, corresponds to the need for a new experimentation. In some cases, it is useful, even necessary, to develop a detection system spatially designed. In this work, we analyzed the very experimental results obtained in recent years, devoting our attention mainly to energy distribution of DST neutrons and their possible anomalies. The energy spectra of DST neutrons have been investigated both at low, less than 0.4 MeV, and at high, up to 4 MeV energies, by means of a microscopic neutron probe. The instruments consist essentially of two detectors, a scintillator type NE213 liquid scintillator, and an helium-3 gas detector, and a dedicated processing unit. As we already told, many instruments commercially available are devoted to the use for radiation protection and medical purposes. It follows that many procedures and algorithms are essentially aimed at the determination of the dose to workers and patients, and many systems are highly automated for the purpose of making them more easy to use, even by non-specialist staff. It is necessary, therefore, to extract from the several options offered by an automatized system just the one useful for the better understanding of a particular physical problem. You can see here a region in low energy and a region of high energy. A few tenths of keV, a few hundred of keV. This is something strange, anomalous. From experimental data, we can see that GSP neutron production is not uniform in energy. Similarly, and it is possible to hypothesize in connection with their time asynchrony and spectral anisotropy. For comparison, we can see the calibration spectra performed with microspect 2 with some facilities of such a nuclear center, nuclear research center. Thermal, we say we can see reactor trigger with this flux, then fast neutron reactor Pepino, and then americium neutron source. There are important differences as we about the other just mentioned. This is important. We must underline that the encounter differences are integral part of our research. Why? We do not walk along the main road that, from an historical point of view, stems from the discovery of natural radioactivity. On the contrary, starting from the deformation of space-time, we observed certain reactions. In other terms, deformed space-time shows a new way to produce nuclear reactions. Difference, small, great, however difference, encountered along a different path. Here are some examples. They can seem trivial, but I sometimes like to express myself by I imagine. You can see the images are presented just to illustrate only a loose analogy. In the slide are presented some images. A map of the Alps will indicate some of the main route of passage. A cyclist who is resting after having climbed with great difficulty in the mountain. It's obvious that change across the Alps in different points. By different means, it is natural to expect some difference in space and time and energy. This is almost clear. But some other images, a tunnel, this is Mount Blanc, and a viaduct. Let's go further. Consider that to carry out works to facilitate the crossing of the Alps, tunnels, viaducts, and so on. In short, trying to make, at least locally, the mountain as flat as possible. For doing all this, it was necessary to spend energy. Coming back to physical problems, and especially to the production of GSP reactions. Now, let us consider that we have spent the whole energy available in producing space-time deformation necessary to obtain a nuclear reaction, in this case, neutron emission. At this point, there is no residual energy, no radiation of the energizing. Therefore, no gamma rays emission occurs. It's a very simple, but it is an explanation derived from the theory. We never see gammas, no, just a moment. But point out that we do not observe gamma rays connected to the excitation of the energizing, as we refer. Sometimes someone says there is no radioactivity. But however, the theory of deformed space-time does not at all exclude the emission of other particles or radiations. And we have seen. So, in particular, in the case of radiation that involve high energy gamma radiations, we should consider the process of production of electron-positron pairs. Consequently, we should expect the emission of gamma annihilation radiation. Let's see these images. It's possible to see. However, in the upper figure, there were classical 511 Kelvin for the two rest mass of electron and positron, and in a general case, the sum of the rest mass of the two particles. Why I say this? For the argument is even now a subject of our research. Let us return for a moment at the beginning. We started by pointing out certain anomalies found in the ST neutron. The emitter inverse, the direction emission, the neutron emission is asymmetrical. The gamma emission accompanies, no gamma emission accompanies the emission of the neutrons. What can we say now? Now we may state that even in the energy distribution, neutron DST shows some anomalies. We can think this is perhaps we would imagine something like this, for they are strange in space, strange in time, and so on. It is to imagine that even in energy there is some anomalies. But this, I think, is the first time they were measured. In conclusion, in a few years, we have made many important steps forward. The ST neutrons, with their peculiarities, have become an objective fact, and a fact experimentally proven. We do not say they exist, do not exist. Proven. Are strange, there are anomalies, and now we measure even their energy distributions. So, we started from the simple fact the existence of such a neutron. We were then able to characterize them as regard with their characteristics in space and time. Finally, we performed for the first time measure of their energy. Now, we can say for the first time we have a global characterization of the neutron. There's, we go further. There's a new experiment not yet presented published. Are so strange as a neutron, learned by our experience, we try to put our detectors in a position where and more intensity, so to have the possibility of trying an absorption measure. And then we interposed a 4 centimeter of boron acid, boric acid, between the source, we say, of neutron, and a detector. The effect was the completely disappearing of neutrons on the detector. Showing this that there is a slowing down of neutrons passing through hydrogenated materials, and when thermalized, there is final absorption in boron. That means that they are strange as you will. They are strange in neutron, but they are certain neutrons that undergoes the normal behavior of neutrons. I'm not finished. Are we proud of this acceptance? But there is another thing. It's only a little part of the problem. Consider the matter as a whole. There is a problem. We have before us new phenomena and new problems, and we are called to give answer. Oh, I presented you only images, of course. If we come back to the origin and to the text of the theory, you can see that this only the book and only the first page, the front page, is full, is completely full of formulas and mathematics and so on. I prefer to not to use formulas and going with images. Something you know that I'm a painter too, so I like very much to explain myself by graphics, and what I don't be able to understand in a way I try to guess by imagine and by artistics. So it's a strange thing, but it was acquainted since I was a boy, so it's important. We can say this. Oh, I said it very badly, but this is right written. The presented slides wish to be only a brief introduction to the problem. All technical aspects and fundamentals are widely covered in the publication cited in the references attached at the official text of this work. And to finish, a glance of a landscape to me dear is the Lake Wolfsena near Viterbo, the town where I live and work. Thank you for your kindness and your patience.
Thank you. Any questions? Anton?
I was very intrigued by your talk and the earlier talk as well on the same subject. Now, I come from a belief of a Euclidean space, so space-time doesn't go into my belief system. So the deformed space-time is even further away to what I think. May I just ask the question, when you did these tests, have you ever looked at this photographically to see the little sparks coming off, that it could be electric discharge, that there is a high voltage produced locally, which they would like a thunderbolt to come out and be part of this? So if you put your steel sample, which you had in the ultrasound. Are you following what I'm saying? You know, that you look at this photographically to actually make a photograph of the event when it happens, to see if there's electrical discharge.
You mean spark? Sì, ci sono delle scariche elettriche durante gli esperimenti.
There are two kinds of experiments. One, the type of experiment has ultrasound.
Yeah.
Another, we have the discharge of electric discharge. Yes. But we prove with other instruments and to avoid the influence of, for instance, microwaves and so on. The measure of absorption of the neutrons was made more for this purpose, to make to be sure that there was not an influence of electronics and so microwaves and so on, but they were really neutrons, for they were flowing down in hydrogenated materials and then stopped in bodies.
I understand that. I'm not questioning the neutrons. I'm questioning the process of neutron formation. When you said when you detect a neutron, you don't detect the gamma ray that is normally associated with a decay that gives a neutron. So that energy needs to be somewhere else. So is it, what I'm saying, could that energy be electrical energy, which then on the surface of the material will make a lightning bolt come out of the material?
Problem for the neutron spectrometer are so complex machines that and they are aimed especially for those for sanitary aims. It is there is some difficulty in this. For instance, if you consider a dose in gamma rays, you only make the sum of the dose. But for neutron, you have to consider that there is a quality factors, and then you cannot sum the energy simply, but the difference.
Il fatto che siccome
use Faraday cage to avoid this possibility. So we are sure that, and we measure it, we are sure there is not an influence or electromagnetic fields.
Anybody else? Well,
I didn't pick up all of the, this has to be both talks, but is the effect increased as you increase the pressure or you increase the, is there a trend? In other words, if you squeeze the iron harder, you get more.
Nel circolo delle concentrazioni ci sono degli aumenti di cambio.
Vedete che aumentano le cose, insomma,
well, it's not a problem of power or energy. Take in mind it is a problem of density in a four-dimensional world. I mean,
No, you're talking theory.
Yes,
I'm asking for an experiment. I'm saying,
Yes,
if you
yes,
turn a
yes.
knob over here, does that happen?
I'm going straight to experiment. This is not like the tennis game. When you hold strongly the ball, you get a more high movement. This is not the nuclear game. In this case, you have an energy threshold. When you cross, not at a time, cross the energy threshold in a four-dimensional volume, I mean energy in space and time, and hypervolume. So, on one side, you have energy density. Take in mind that Newton about square meter is the same as joule or cubic meter. It's the same. So pressure means energy density in space. Power is not energy over seconds, joule over seconds. It's the density of energy in time. When we cross the threshold, we overcome the world of the deformed space-time and the reaction starts. Now, when increasing the power pressure of ultrasounds anyway, we only get the same neutrons in the same way, cutting over the background from outside in any case, both electrical and radiative. And this is all. But the spectra measured during this year for the first time have two main features. They do not resemble any spectra known up to now. Neither from nuclear reactor nor from nuclear sources, I mean americium beryllium sources, the standard neutron test sources, or americium polonium, and so on. So, they are very, very difficult to measure, and in the case of the low energy nuclear reaction puzzle, if you are outside the region, the spatial region, effectively, Professor Albertini and Professor Cherubini showing you the polar diagram around the 360 degrees of the wall emission, and you got the direction where the neutrons and their energy was zero. And you are so unlucky to get this direction, no neutrons, no reaction, no gain. And this is the puzzle of a low energy nuclear reactions. If you are unlucky, no neutrons, no reaction, no gain. And nobody will trust you. This is the problem. And it is not a problem of energy of the pressure, or power of the pressure. It is only a problem of threshold. You must cross the threshold like lies the mirror. From our flat world, the world of measurement, the world of devices, the world of detectors, flat Minkowski, Hamilton theorem of energy conservation, total energy conservation, strictly valid, to the world of nature where it is possible to change the nature of space-time. The world behind the mirror. But the mirror is the threshold. Then the signals cross again the mirror and you get signals in the flat world, in our world, the world of measurements. So there is this problem of two different rules of game. Our world of measurements, their world of phenomena. Now, you don't need to be lucky. You don't need to ask, like Frank Sinatra, like luck be a lady tonight, luck be a lady to a Spaniard. We know exactly from the theory of the deformed space-time which, where, and when are the right direction in space and time, and put the detector there, and there, and when, and then record the measurement. And now the signals are quite clear, well above the background in any case, despite the fact that we, in any case, use the Faraday cage and other devices to avoid any internal noises.
Am I hearing you right? Or just a minute. Are you saying that this experiment only works at certain times of day, in certain times?
No.
No.
In a certain kind of direction and in a certain kind of timing of data recording.
No, I think that what it's trying to say is that you have to...
I beg your pardon, but it is about my
I think that what it's trying to say is that you have to release, you have to reach a certain threshold of energy. So you have to release it with a precise timing. If you have that energy but you don't release it with the right timing, you don't get the effect.
I got it. Okay. Just a semantic problem.
All right. Well,
I'm new to DST. Is it synonymous to define DST with what it says in the literature as an Einstein energy-dependent space-time metric?
Can you say again?
Is DST synonymous with what it calls in the literature an Einstein energy-dependent space-time metric?
No, not exactly.
What's it?
It's Einstein energy-dependent metric. I think it's a global metric. We are involved in a local metric, so
Okay.
with a foreign space-time locally.
That helps. Lunchtime, come back about 2:40.